everybody. I wanted to talk to you today about fractions. So I want to start with equivalent fractions and what it means to be equivalent, essentially. So let me go ahead and pop up a whiteboard here. So the idea of equivalent fractions is really important. I want to think of fractions in terms, I usually think of them in terms of circles. So like if I have one circle, I'm going to think of this as one. Right, one whole circle essentially. So if I have like a half, right, there's two halves there, there's 4/4, etc. Right, and so I guess the first thing I want to say is if I have a over b, right, my a is my numerator and b is my denominator, and the thing that I think a lot of people miss about fractions is that the a and the b tell you two different things. The b, the denominator, tells you how many pieces your whole thing is divided into, and a tells you how many of those pieces you have, right? So if I have 3/4, that's saying that it's divided into fourths, and 3 of them are taken up, right? That's what 3/4 means. So I like to think of 3/4 as like 3 times 1/4, right? It's 3 1/4. And this is going to come in really handy when we're talking about multiplying and dividing. Okay, so equivalent fractions are two fractions that are the same value, essentially, right? So there's my whole one, so there's a half. If I want to call that half 2/4, well, that's the same thing, right? If I had divided this into fourths, well, 2 of them is a half, 2/4. Or I could have called it 4/8, right? Because now I've got 4/8 filled up, etc. I could call it 3/6 if I wanted to, right? There's my half. It could be 3/6 if I just divide it into 6 pieces instead of 8. You get the idea. So the way you find an equivalent fraction is by multiplying the top and bottom by the same thing. So like if I take a half times 3/3, I get 3/6, right? Those guys are equivalent fractions. This is useful because we're going to want to get the same denominators for some things because, like I said, the number in the denominator tells you how many pieces your fraction or your whole is divided into. So here I have thirds, and here I have halves, right? And so if I have like a third and a half, you can't combine those easily because they're not the same size. They're not the same kind of fraction. So like the denominator tells you what kind of fraction you have, and the numerator tells you how many of those you've got. So I can't easily combine a third and a half because they're not alike. It's sort of like with like terms. Like I assume most of you have seen that before, but if you haven't, we'll get there very soon. You can only really add and subtract things that are alike, basically. And so you can't really add and subtract a third and a half easily. However, what you can do is turn them both into equivalent fractions. So for instance, if I turn them both into sixths, right? So if I do this times 2/2 and this times 3/3, this turns out to be 2/6 and this is 3/6. And now, right, so sixths look like this and like this. Oop, I should have just gone all the way through there. They're both whole numbers of sixths, so we can combine those. So that's the basic idea of adding and subtracting fractions, is that you can just chop them up into smaller pieces until they're both the same kind of thing, and then add those up or subtract those. Right, that's the main idea for adding and subtracting that we'll get to in a second. Right, so if I want to do 2/6 plus 3/6, well, we can see that, or if I want to do a third plus a half, we can see that a third is 2/6 and that a half is 3/6. And so now everything is the same type. It's all sixths. And so I have 5 of them. because I have 2 and 3, and so it's 5/6, and that's all you have to do, right? So that's adding and subtracting. We'll do a little bit of an example of that in a second. But that's the basic idea. Equivalent fractions are just fractions that have the same value, but are chopped up into different numbers of pieces, right? So like, well, like I said, a third is equal to 2/6, or it's equal to 3/9, or it's equal to 4/12. And there's an infinite number of other ones that you can choose just by multiplying. Like, all I'm doing here is I multiply the top and bottom by 2 or by 3 or by 4 to get an equivalent fraction. Right, so that's equivalent fractions. You just have to essentially chop the thing into smaller pieces and take more of them. Right, 4/12 is 4 copies of 1/12, which has the same value as 1/3. It's just there's more of these and they're smaller. That's really what equivalent fractions are. What was the second point I wanted to hit? I'm sorry, I've lost my train of thought there. Whoop. It was, oh yeah, least common denominator. So the way you find least common denominator, so like I said, when you're adding and subtracting, you want to get common denominators, because that tells you that your fractions are the same type then. So the way you get the least common denominator, because that's the smallest one and usually the easiest to work with, not always, not 100% of the time, but usually the easiest thing to work with. The reason you want least common denominator is so that you can add your add or subtract your fractions. You don't need this for multiplying or dividing, by the way, but yes, for addition and subtraction. So least common denominator is abbreviated LCD. And it is the smallest denominator that you can use for 2 different fractions, or 3 or more if you wanted. So like, let's do 3/5 and 7/10. Right, so if I wanted to find the least common denominator there, what I need is some denominator that is a multiple of both of those, both 5 and 10, so that I can get them to be alike. The easiest way to find this, not necessarily the best way, but the easiest way is just to multiply them together, right? So 5 and 10 both go into 50. And so I could use 50 as my least common denominator, or as my common denominator if I wanted to. It's not the least one, right? And to get 3/5, to turn 3/5 into 50, or into some number of 50ths. Sorry, let's undo that 1 second. There we go, 3/5. I would multiply by 10/10 to get 30/50. And that is equivalent to 3/5. And you could do the same thing with 7, multiply the top and bottom by 5, and you get 35/50, right? And now I could combine those, right? Now I have 50ths, and I have 30/50ths and 35/50ths, so I would add them together to get 65/50ths, and that all works. It's not the easiest thing to do, though, because those numbers are bigger than they need to be. It's much easier to instead, here, let's get rid of this. It's much easier to instead, oh, shoot. Sorry. There we go. To instead find the smallest number that 5 and 10 both go into, which is 10, right? 10 goes into 10 one time, and 5 goes into 10 twice. So I would have to multiply 3/5 by 2/2 and 7/10 by nothing, right? So the easier way to do this, because the numbers are smaller, and then I have 7/10. That's supposed to be a comma in the middle there. The easiest way to do this is to find the smallest number that both of these go into. Now, sometimes that can be a little bit of a hassle, but I'll show you a way to do it. It gets a little bit awkward, but I'll go ahead and show it to you anyway, because it's the kind of the most general way to do it. Usually, you can just think about like what number both of these things go into and come up with one pretty easily, right? You got, what, 12 and 18, you could probably come up with 36 just by going 12, 24, 36, 36, right? But when you can't, you can do something like this. So I'll use the aforementioned 12 and 18 in case that, in case you don't just immediately know off the top of your head that 36 is 18 times 2. So if I have 12, let's say I have 1/12 and 5/18, and I want to add them together, right? I want to do this, 1/12 plus 5/18. Well, as we know, 12ths and 18ths are not the same size, and so we can't just add them together. So what we have to do instead is figure out some number they both go into. And like I said, it's going to be 36, but let's see how we come up with that. So what I'm going to do is find the prime factorization of 12 and the prime factorization of 18. And prime factorization just means pull primes out of it. You might know this is a factor tree. So multiply any two things to get 12. So I'm going to do 2 and 6. I like to pull out small things on the left and then whatever's left over. Like the smallest thing I know of that goes into 6 is 2. That leaves me 3. And then all these numbers here, 2, 2, and 3 are prime numbers. And same thing for 18. So 18, the smallest thing that goes into 18 is 2. And that leaves me 9. Smallest thing that goes into 9 is 3. That leaves me 3. And all those guys are prime numbers. And so this is 2 times 2 times 3. And this is 2 times 3 times 3. And so what I need is some number that has all of these factors in it and also all of these factors. So my preferred way to do that, and you can get some math book to explain it to you a different way if you want, but the way I like to do it is I like to just start with one of them, right? So my LCD, I'm just going to start by throwing in 2, 2, and 3, and then ask myself, all right, now what am I still missing from this? The 2, I got a 2 in there. That's good. I got a 3, 3's in there, and then I have a second 3 that I don't have yet. So I'm going to throw in a second 3. And that's 36. If I multiply that all together, 2 times 2 times 3 times 3 is 36. And so that's my least common denominator. You just start with one of these and then throw in all the prime factors that you're missing. And if I'd started with 18, it would have worked exactly the same. I would have had 2 times 3 times 3, and then I would realize, oh, I need a second 2, and put in another 2. Now, one thing that's nice about this is that this tells you what pieces you are missing and therefore need to multiply by. So 2, 2, 3 is 12. So that means that this part of this is 12. And so my 1/12 up here is missing a 3. So that's the thing I have to multiply by. Right? So this is going to be 3 times. Similarly, this guy right here, my 2 times 3 times 3, that's 18. So the thing that my 18 is missing is whatever's not in this circle, right? It's the 2. So I'm going to multiply by 2. Oh, excuse me, I wrote 3. I meant to do it this way. I apologize. 2. This should be no, I don't want it clear. Let me select this. Sorry, Zoom's a little awkward here. That close this, reopen it. Okay, so my 3/3. This should have been 3/3 from the beginning. Right, so I'm multiplying by whatever I'm missing for my least common denominator. So when I do that, then what I end up with is this. This is 3/36 plus 10/36, and now those are both over the same denominator. So those are the same type of fraction, right? And I have 3 of them in the first case and 10 of them in the second case. So if I have 3 1/36 and 10 1/36, that gives me 13 36. Right? So that's how you have to add and subtract fractions. You have to get them over the same denominator so that they are of the same type. Otherwise, you can't just subtract them. Like, it's very tempting. I know some people look at this and say 1/12 plus 5/18. Well, you just add straight across and get 6/30. That's totally wrong and never works. Like, that's just not gonna do what you want. You want to do this, you have to make them all look alike first, or be of the same type, I should say, first. And that's why you want common denominators, by the way. Now, you don't need common denominators if you are multiplying or dividing. So let me talk about multiplying, because dividing is really just multiplying. So multiplying goes something like this. Like, let's say I have 7 over 10 times 3 over 4. What you can do, and this works just fine, just multiply straight across. This works, 21 over 40, right? That is the right answer. That's what you want to do. The reason for this, and I'm going to introduce a really important sort of math word here, which is of. I'm thinking of this as 3/4 of 7/10. Of generally means multiply. When it comes to percentages and fractions, of almost always means multiply. Like you can construct an English sentence involving numbers where of doesn't mean multiply, but most of the time it does. So for instance, let me go back to my circles here. Circle. If I wanted half of this circle, there it is, half. The whole circle is 1, and I'm thinking of taking half of it, so I'm going to multiply by a half. It gives you a half, unsurprisingly. So I'm thinking of this as 3/4 of 7/10. And if I want just the mathematical way to do that, multiply straight across, reduce if necessary. I said that you actually want to do that in the other order. You actually want to reduce first and then multiply, just because it makes it easier, which we'll see in just a second. But that's the basic idea. Of usually means multiply with fractions. So if I want like, I don't want to say this. If I want like a third, undo. Let's say I wanted a third of 9, right? So I do 9, and then I wanted a third of that, so I'm going to do times a third. I think we all know what a third of 9 is. A third of 9 is 3, right? It takes 3, or it takes, if I have 9 things, and I want a third of them, well, that means divide them into 3 pieces, and then take one of the pieces, right? So we've got number of pieces, and then how many we want. Sorry, everything's in the way. Right, so I divided into 3 pieces, so there's my 3 pieces. And then I want one of those 3 pieces, so I just pick one, right? So here's the one I picked, that one right there. And there are 3 things in there. So that means that 1/3 of 9 is 3. So 9 times 1/3 is 3. And multiplying fractions wise, that's basically all there is to it, right? The denominator tells you how many pieces you're dividing into, and the numerator tells you how many of those pieces you want. So that's the conceptual way to think of it. The like doing it on paper way to think of it is you literally just multiply straight across. So for instance, let's do something a little harder, right? So if I have 17 over 18 times 6 over 5, right? So I'm taking 6/5 of 17 over 18. Now, there's a couple ways to think of that. The way I think of it conceptually is I'm thinking of it as I'm dividing 17 over 18 into 5 equal-sized pieces, and then I'm taking six of those, right? So actually more than one of the more than 17 over 18. And that's what I'm thinking in my brain, but I'm not going to do that on paper, because taking 17 over 18 and dividing it into 5 pieces is kind of a hassle, right? I have to do 17 over 18 times 1 over 5, and then that times 6 to know how many I've got. The easier thing to do mathematically is this: cancel first. So actually, let me do it the long way once. So this is going to be, if I multiply just straight across, 6 times 17 is 102. And 18 times 5 is 90. And that is right, but not as nice as it could be. Because what we're going to want to do then is reduce that fraction, right? And so I could cancel a 2 out of the top and bottom, in the same way that I can multiply by the same number on top and bottom, I can divide by the same number on the top and bottom, 51 over 45. And then I don't know if it's obvious to you or not, but 3 goes into both of those things. 17 over 15. And that is the right number. However, there's a much better way to do it. And here's the better way. What I can do is do all that canceling before I multiply while the numbers are still relatively small. I can notice that 6 goes into 18 and then divide a 6 out of the top and bottom. Now, usually the way we write that is something like this, where I'm going to cancel a 6 out of the 18, leaving a 3, and cancel a 6 out of the 6, leaving a 1. And then when I multiply, I'm multiplying 17 times 1 and 3 times 5. And that's easier. That's just less work. And so that's what I want to do most of the time. When I multiply by fractions, that's actually the first thing I'm looking for, is what can I cancel? Because I want to make things as easy as possible. And that's the easiest way, essentially. So you want to cancel first. You can cancel later. It's not wrong to cancel later. It's just harder. And so I prefer not to. I prefer to cancel first when I'm multiplying. And then dividing, well, let's look at what that looks like, right? So if I'm going to do, let's say, 4/3 divided by, let's do 11/6. The thing you want to see here, I want to go back a second. When I said 1/3 of 9, right? That was 9 times 1/3. What I did there was I divided 9 into 3 pieces. That's exactly the same thing as 9 divided by 3. And that relationship of 1/3 being 3 over 1, but flipped over, is exactly the same relationship that dividing always has with multiplying. If I want to take 1/3 of 9, I can think of that as 9 divided by 3, and it works just fine, right? Those are actually the same thing. So the easiest way, if I wanted to do 9 divided by 3, I can also think of that as 9 times 1/3. If I wanted to do 10 divided by 5/2, what I can do is the same general idea of whatever you're dividing by, just flip it over and multiply. Right? It's probably easier to think of 9 divided by 3 than 9 times 1/3. But if you have 10 divided by 5/2, it's going to be way easier to think of it as 10 times 2 over 5. Basically, if your number starts as an integer, it's probably easiest to just leave it and do the operation. If it starts as a fraction, it's going to be easier to flip it over. It's called taking the reciprocal. Flip it over and then multiply, because multiplying fractions is really simple. Multiplying fractions, again, just straight across with some canceling. So if I want to do that up here, 4/3 divided by 11/6, the easiest way to do that is 4/3 times 6 over 11. And then I can cancel this and this, right? Take a 3 out of both of those, and I get 8 over 11. That's your basic idea when you are dividing fractions, is flip over whatever you are dividing by and multiply, right? So notice, by the way, if I had flipped over the 3/4 or the 4/3 rather than the 11/6, I would get something different and it would be wrong. You want to flip over the thing that you are dividing by. Another way you can write this, by the way, which a lot of my students absolutely hate, is in big fraction form. I can't tell you how many times I've taught this exact class and had people get scared off by something like that, 4/3 divided by 11/6. This and this are exactly the same. There's literally no difference between them. If you see this, get scared by it, and think to yourself, oh my God, what do I do? Well, just do this, right? The thing on the bottom is whatever you're dividing by, flip that over and multiply. So this goes to this, 4 over 3 times 6 over 11, and then you get that 11. So you can write division either way. Don't get scared by it being big like this. Doesn't matter. You can think of it like this just fine, right? When you see this, don't say 4 over 3 over 11 over 6. Say 4/3 divided by 11/6. And then your brain, I hope, will go to this, and then it'll tell you, all right, well, I just need to turn over the second one, and then it works fine. And that's dividing fractions. And the last thing I want to mention is simplifying fractions. So let's take something really big. Let's say I have 64 over 360. And I want to simplify that. I want to basically get an equivalent fraction, but smaller with where the numbers aren't quite so big. And what I can do is I can just repeatedly divide out something that I know goes into both of them. So for instance, I can divide a 2 out of both of them, right? Because they're both even. That's always the first thing I look for, by the way. Is the number even? Take a 2 out. So if I divide 2 out of 64, I'm left with 32. Divide 2 out of 360, I'm left with 180. And then I could do that again. They're both still even. So I'm going to make this, so that's going to be 16 over 90. They're both still even. So I can do that again. So this is going to be 8 over 45. They're not even anymore. And then 45 is 5 times 9. And 9 is 3 times 3. So this is 3 times 3 times 5. And this is 8. None of those things are the same. So I can't cancel anymore. Now, that process is fine. It's one step at a time, and you just do a bunch of steps until everything's until all the like factors are canceled out. There's another way to do it, which is all at once, which is actually my preferred way. So let me show you that. And so I'm going to find the prime factorization of both of these, 64 and 360, by doing the factor tree. So 64. Smallest thing that goes into 64 is 2. 32, and 2, 16, and a 2 and an 8. And that's 2 and 4, and 2 and 2. All right, so 64 is just a bunch of 2s. 360, I can take 2 out of that, and that leaves me 180. And 2 out of that leaves me 90. And 2 out of that leaves me 45. And 45 doesn't have any more 2s in it. It's 5 times 9, but the smallest thing that goes in is 3, and it leaves me 15. And 3 and 5. And so I can think of this as 2 times 2 times 2 times 2 times 2 times 2. There's 6 of them. And then 360 is 3 2s and 2 3s and a 5. And I can just cancel everything that's alike. And that leaves me 2 times 2 times 2 over 3 times 3 times 5, which is 8 over 45. And I know that this is all the canceling I can do because the top is all 2s and the bottom, or the top and bottom don't share any factors. And that's great. You've probably seen this before, I would imagine. Where you may or may not have seen it is with variables, right? So this is algebra, we're going to be using variables, not just numbers. And so if I have something like, let's say, 14xy squared z, and let's do 35x squared y, right? And I wanted to simplify that, I can, and it's actually not any different than the thing I just did a second ago with prime factorization. So what I'm going to do is I'm going to take 14 and think of it as 2 times 7, those are both primes, and 35 as 5 times 7. So this is really 2 times 7 times x times y times z, right? Y squared is just y times y, that's all it means. And then 35 is 5 times 7 times x times y. And then I just cancel out all the things that are alike. The fact that they're, represented by 7s or x's or y's doesn't matter. If they're alike, they get canceled. Right, and that's all there is. I can't cancel anything else because there's nothing else left alike there. Let me make sure that that's all I wanted to say about fractions, but I kind of think that was it. Yeah, that's all I wanted to say about fractions. So those are the operations that we're going to be doing quite a bit of with fractions. I guess, actually, I'm sorry, there is one more thing I want to say. It's not a thing we're dealing with yet, but we will be, and it's probably the single most common mistake people make in intermediate algebra, which is this. If we had like x plus 3 over 2x minus 1, what people will often do is try and cancel the x's. Do not do that. That does not work. And the reason that does not work is that there's still addition and subtraction up there. So you can cancel multiplication with division. Notice over here, everything is multiplied, and then I can cancel stuff. Same thing on the previous page. Everything is multiplied, and so I can cancel. When you've still got addition and subtraction here, don't try to cancel it. It has to all be multiplied first, and we'll deal with that much later. That's in chapter. I don't remember which chapter it is in this book. It's much later in the course when we do rational expressions. But when there's addition and subtraction, don't try to cancel, right? Like, and here, let me give you an example. Let's say I had 55 over 11. All right. I think it's clear that that's 5. I hope that's obvious. Right, 11 goes into both of them. I end up with 5 over 1. That's 5. What if instead I did this? 50 plus 5 over 6 plus 5. Right, 11 is 6 plus 5. Now again, I can't do this. Right, this is not legal. But I could, oh, the 5s cancel. Oh, and then I can take a 2 out of the rest of that. 25 over 3. And of course, that's entirely wrong. Right? It looks silly when I do it this way. I hope it looks silly to you. It should. It looks less silly when it's with letters because you can see two things that look alike and want to cancel them. But this is dumb. Don't do this. Right. Another way to think of it is, let's say, what if I had like 123 over 42, and I said to myself, aha, I can cancel the 2's. Right. That's dumb. Don't do that. That's not gonna work. So when there's still addition or subtraction left, don't try to cancel anything. That's the last thing I want to say about fractions. Make sure it's all multiplied first, then you can cancel. But don't cancel if there's just addition and subtraction. All right, that is the last thing I want to say about fractions, and so I don't want to drag this out any longer than it needs to be. So I will go ahead and stop the video now, and I will see you guys in the next one.